So now we're going to talk about how the operating system creates files. And we did this for Windows for both FAT and NTFS. So there are going to be some parallels here, but there is actually quite a bit of difference though. So the following steps briefly describe how a file is created in Linux. First, we want to create a file, let's say /hello/hi. Okay, so the OS reads the superblock data structure, discovering the block size, and on most systems it's going to be 4096. Then the operating system reads the group descriptor table, which tells us the layout of each block group. Okay, and as you can see here, there's a capture of using istat to find all this information out. Okay, istat is once again a Linux utility that you can use for this. Okay, so let's take a look at a live version of that. So here, my main hard drive partition is SDA1. So it comes up with all of the information about it. And here I can see the block size, the number of links, and so forth. So really, all the information I might need to kind of get started. Okay, so here's the next part of it. On my machine and Derek's machine, Derek is the one who did the captures in PowerPoint, and I showed you just recently my own live use of istat. But anyway, the root directory is in inode 2. The group descriptor tells us that inode 2's information can be found in direct block 9249, and that's actually the exact same as my Ubuntu virtual machine was. So same exact things. I had a different number of links and different times, but essentially the information was almost identical. Okay, so let's continue on. First we got to read block 9249. This is going to tell us everything that's in the root. Okay, we now update the access time to indicate that we have accessed this inode. That's what's going to happen. We search through everything in the root, and then we see that the inode of the /hello folder is 694.6817. Okay, and you can see that below. We then move to inode 694.6817. The group descriptor tells us that inode 694.6817's information can be found in direct block 277913. So you'll notice that on my live system, my VMware system, it's going to be a little bit different than what Derek was showing. So if I do this, you'll see that my hello directory is in a different inode, which makes sense because once you get files written and read from and moved around and stuff and expanded and truncated, nobody's machines are going to be the same. Okay, so we read block 9241, which enumerates everything in the root. We now update the access time to indicate that we access this inode. Okay, we search through everything in root. We see that the inode of /hello is 694.6817, and as I showed you, it was different on my VMware install. We then move to the inode at 694.6817, and the group descriptor tells us that its information can be found in direct block 277913. We read block 277913, which tells us that there are no files in the directory. So we wish to allocate an inode for a new file, which we will call hi. We search for an unused node, Conveniently, we find one in the same block group as the folder hello. This inode is 694.6820. We append the directory listing for hello with hi and the inode 694.6820. We search for a free block. We find one at 126.7823. We mark the inode bitmap and the block bitmap as used. The addresses are added to the direct pointers. The group descriptor and superblocks have been updated. Free block counts in the access time and the data are modified. We then write the content to the disk. Okay, so here's a diagrammatic representation of file creation and where all this information is coming from. So we have the superblock, and remember there are copies of that throughout the file system. And we have the group descriptor table. Finally, we have the groups of blocks, the block groups themselves, 0 through whatever it turns out to be. So each block has an inode table. Okay, and then there is some sort of content, whether it's a root directory or the actual contents of a file or whatever it turns out to be. Okay. In addition, you'll see in block group 2 there's the block bitmap and the inode bitmap. And the only thing that these are doing is saying which block bitmap, which blocks, and which inodes are in use. Okay. So you also see the directory contents and their representation, the dot and the dot files, which represent the current directory and the parent directory. There's the length, the file name, the inode number. And you'll notice that the length of 12.jpg. So I want you to notice, at least for right now, that in the dir1 contents there are three files that all have a length of 16. Okay, so now that we've talked about file creation, we can talk about deleting files, and we'll get started with that. The following steps briefly describe how a file is deleted in Linux. Okay, so we want to delete a file, let's say maybe the one we just created, /hello/hi. Okay, we read the superblock data structure, and that's how we started to create the file also. We get the block size. Here again, 4096 is going to be the most common, although it doesn't have to be that. It can be set to something else. Just like in Windows, the cluster size can be something other than 4096. Then the group descriptor table is read, which gives the layout of each block group. Okay, so these are sort of the getting started things. And one of the nice things is that most operating systems, Linux included, basically is going to cache this information. So it's not like it's going to the disk every single time it needs to read a superblock or the group descriptor table. So sometimes, or most of the time, those are going to be cached by the operating system anyway. Okay, so here again, the root directory is on inode 2. The group descriptor tells us that inode 2's information can be found in a direct block at 9249. And this is just what we saw as we looked at it before. You read block 9249 and it enumerates everything in the root. So we now update the access time to indicate that we access this inode. We search through everything in the root. We see that the inode of hello/hello is 694.6817, the same as it was before. Then the operating system moves to 694.6817. The group descriptor tells us that inode 694.6817's information can be found in direct block 277913. I'm going to skip these next two bullet points because really they're duplicates. So lastly, we read block 277913, which tells us that there is one file in the directory with inode 694.6817. This time we remove the entry from the directory. We then decrement the link count in the inode by 1, indicating that the inode needs to be deallocated. We deallocate the inode and mark it as unused, and if we are using ext3 or ext4, we remove the link to the block. Though the inode is marked as unused and the link to the block is removed, the file is still there, just like it is in Windows. The file itself, the file data, file contents are not removed. But there is no way to directly retrieve it. In ext2, the inode, while marked unallocated, still points to a block, which makes data recovery much easier. So here's a functional diagram of file deletion. So we still have the super block and the group descriptor table. And essentially it's doing the same thing, looking at the same data structures, whether you're creating or deleting or removing a file. So this shows that graphically. So there are a lot of ways that you can actually search a hard drive for evidence. Let's say you want to prove that a criminal visited a particular website. This could be a daunting task. You could look through their entire history painstakingly. You could also request DNS records. This would take time and probably be some red tape, but you could also search for strings matching a particular phrase on a disk. So for instance, you could use the grep command as follows: sudo grep -a, and then whatever you're looking for, how to bury a body. Then the device, and you would go ahead and redirect it into some sort of a file that you can then read. Okay, so let's take a look at a real-life example here. And let's say sudo grep -a free dev sda1, and pipe that into, we're going to say home or Lineker desktop search.txt. Okay, and this is going to take a while because it's looking through the whole hard drive, so I'm going to hit pause for just a minute here. So just as an aside, that grep I did somehow got hosed up. I'm not sure if my Ubuntu instance is hosed up, but here you see search.txt gave me 94 megs. And if I do cat search.txt, it's really quite a bit of data, binary, and so forth. So something got hosed up, and I'm not exactly sure what happened, but Ubuntu, before I had even done that, had given me some sort of error message that it encountered a serious error. Okay, but back to our previous example. So let's say that there was a saved file on disk with the phrase how to bury a body, and then that file got deleted to thwart the police. And here you can see the results of doing that. There's a capture of this process. Then you can actually run that grep command to see if you can actually find something, and it actually shows up even though it has been deleted. So you can also use fstrim on SSDs to thwart file recovery. You can use GNU shred. We've kind of already mentioned that a bit. You can run dd and take input from the file. This will actually zero the drive. You can run dd and take input for the file. This is what utilities such as dban does. So there are ways that you can actually prevent file recovery even though you've deleted the file. So let's talk about fstrim. fstrim discards unused blocks. So this is a really nice optimization program that can help you save disk space and make everything work better. SSDs tend to degrade performance over time because unlike hard disks, they have to zero out the sector before they write data to it. Okay, fstrim zeroes out these sectors so that the SSD can write to it without having to delete unused data beforehand. Doing this means that the data in unused blocks are irrevocably lost. So in other words, if you had any data there that you had thoughts of recovering later on, they've already been zeroed out. So GNU shred, this is a command that you can get. It destroys data by overwriting it with gibberish. Okay, so we're going to take a look at both of those right now. So there might be times in order to do some anti-forensics you might want to modify partitions. So you can use the parted utility. So you can delete a partition by using rm and then the number, where number or pound is a partition you want to delete. To resize a partition, use resize part, and to create a new partition, use mkpart. Okay, and here you can see a capture of using this utility. Okay, parted. So after you've created a partition, you still need to format it. Until that happens, the data from the partition is still there. Okay, so even though you may have created or deleted or moved or whatever, there's still data there, and you need to format it in order to zero out that data. So unless we actually do a full format, the data will still be on the disk, just unallocated. It's almost like we had deleted the files but left them there. This is why it takes so long to do a full format. And this is actually true on Windows too. A lot of times when you come up with the format in Windows, it says quick, or you can either select or deselect quick. And you'll notice that if you deselect quick, it really does take a long time. Even for like an 8 gig flash drive, it's really going to take a significant amount of time. So here's how we can format partitions. MKE2FS. Okay, and so we can also use DD to zero out whatever's on the drive. So now let's take a look at file recovery. We can actually use data recovery utilities such as testdist to repair a corrupted partition. Testdist searches each cylinder in an attempt to find partitions, which it then tries to salvage. Photorec is very similar to the other file carving tools we've used. Simply select which partition you want to find files from, and it'll find files for you. Okay, so let's take a quick look at Photorec. Okay, so the first thing I have to do is select the media. And SDA is my main drive. So it's Linux. So it's going to take a lot longer actually to look at everything from the whole partition. So we're just going to scan for unallocated space. And I'm going to go to desktop since I had deleted that search.txt file. Okay. So here it shows you all the files. and you can explore those and go ahead and take a look. Okay, so here are some captures of the process of using Photorec that are in the slides. So first we have to select which disk we want to use. Okay, you've already seen that. Okay. So it assumes that the partition is so damaged it can't be read. So it doesn't know what partition you're using, therefore it will ask you. Okay, and you saw me doing that. Okay. So now it goes through the recovery process and takes care of everything for you. The files, usually without file names, are stored in the directory you specified. Okay. And for this, you'd be a lot better off storing them, say, on your maybe a flash drive or something, and you won't actually name them. Okay, so files need to have some sort of permissions, and they all have their own permission settings, whether they're a directory or an actual file. And Unix permissions have been around a very long time. In fact, the very first version of Unix had a chmod command, which we use today and we all know and love. But permissions are based off of the idea that there are three different scopes. User permissions, which is the owner of the file. Sometimes people say owner permissions. Group permissions, the group the owner of the file is a part of. And everyone else, or other permissions. So you can give permissions to be granulated for the owners, separate from the groups, separate from everybody else. So permissions are set by octal bit fields with combined values of 0 to 7. The rightmost bit specifies execute. So if the rightmost bit is 1, that group, the owner or that group or everyone else has execute permissions. The middle bit specifies write access, which means you can write or modify a file. And the leftmost bit specifies read access. So notice that the middle bit the rightmost bit has a value of 1, and this translates to 1 decimal. The middle bit is 010, which has a decimal value of 2, and the leftmost bit has a decimal value of 4. So these actually combine to values that are 0 through 7. The combination of these different bit fields produces different permissions. So let's ask the question, what combination provides execute and read access? Well, that would be 101. The leftmost bit being 1, the rightmost bit being 1 for execute. So this is a combined value of 5. So the leftmost octal, the first number in a permission, will specify the rights the user or owner has to the file. Okay, and take a look at this capture from down below in the slide. Now, for right now, just ignore the D because D stands for directory. But to the right of that, the 3 digits you see, RWX, those are the permissions that the owner has. The owner has read, write, and execute. And just to let you know, for a directory, you have to have execute even just to look inside of the directory or change to inside of that directory. The middle of these specify the rights of the group. So let's see, owner has read, write, X, but group has R-X, meaning read, no write, execute. The rightmost octal specify the rights of everyone else. So to the right, let's see, so you go owners 3, group 3, and then everyone else's 3 is R-X. Actually, for the output.img file, it's R-, and for everyone else, and for the group, it's RW-. Okay, so you can take a look here, and it shows you the groupings of those file permissions. So we can use chmod to change the permissions. Here, chmod is going to set the owner's permissions to 7. That's all 3 bits. The group's permissions to 6, which is a combination of 4 and 2, which means read and write, but no execute. And 4, which is just 4, which just means read. 7 means the user can read, write, execute. 6 means the group can read and write, but not execute. 4 means everyone else can only read the file. Okay, and the output.img below, you can see it reflects these values. So there's a more human readable way to talk about these permissions if you're using chmod. Chmod, you got to figure out the bit fields and everything. If you'd prefer, you can set permissions the human readable way by specifying +x plus r plus w to chmod. So if you want to make everything, if you want to make a file executable for everyone, you can say +x. This is actually more complicated than just figuring out the numeric notation. So here's an example using chmod with +x. So chown is another very powerful and useful command. Chown means change ownership. The chmod is changing the permissions. Chown is actually going to change the ownership itself. So it changes the ownership of a file or a directory from one user or another. You can also specify the group name. Chown modifies the inode and updates it with new permissions. So here's chown in action. So you want to use sudo. So sudo chown root new test, and you're going to probably have to give your password. And then if you take a look at it, now you can see that the owner has been changed . And if you look at it, you can see that the owner has been changed. So then if you go ahead and run istat, you can get a lot more information about it. And this is going to show you not only the size and the group and so forth and the inode number, but it'll show you that other information, such as the number of links. Notice that the UID changes. Okay, so you can see that the UID has changed from one to the other. Okay. chmod, change file mode bits, it allows us to modify the permissions to a file. So we've kind of already mentioned this. So there are 2 ways to modify a file. We can use the bit mask, which is a combination of those bits. First number is for the user or the owner. Second is for the group. Third is for global or everyone else. So if you want to give everybody full permissions, you would just use 777. Or we can use the human readable arguments plus RWX. So we have already actually used DD in this class a good bit. We used it to both create images from our USB drives, and it doesn't have to be a USB drive, it can be really any drive. And we also use it to restore to a USB drive. So it's a really strange command, and its strangeness is based on some of its history. DD was originally used for converting between IBM's EBDIC and everyone else's ASCII character encoding standard. DD inherits the syntax from IBM's Job Control Language, or JCL sometimes. By default, DD is designed to read from standard input and write to standard output. And we specify what we want to do with this output. Today, though, we primarily use DD to do a bit-by-bit copy of the disk or partition. If we use IF to specify the input file, that is where we'd like to take our input from, rather than a standard input, we use OF to specify the output file, that is where we'd like to place output to rather than standard output. Okay, and here you see an example of exactly what we've been doing the last month. Sudo dd if equals whatever the device is. Okay, OF equals whatever the file is you want to save to. And here again, you can have a fully qualified path if you want, or you can just have a relative path such as output.img. Now, depending on your system, I have found that to image an 8 gig hard drive usually, or excuse me, an 8 gig USB drive usually takes about between 5 to 10 minutes. It actually takes a lot longer to wipe a USB 8 gig stick. And by the way, DD can be used to wipe the wipe stuff too. It's actually a DD command that does the wipe. So DF is designed to report file system disk usage. Okay, so this is, and as you can see down in this capture, it's got all the devices and all the different important things that are on the system. It shows you how many blocks you have, what's been used, how much is available. It gives you a use percentage, which is actually really nice. It's a lot easier to see the use percentage than to have to sit there and figure it out yourself. So DF is useful for showing the amount of disk space available on the file system, as well as listing all the disks that are mounted. The problem with DF is that it doesn't show unmounted disks. You can actually go to the file manager in Paladin to do that and to show that. It will actually show you stuff that's not mounted, and you can actually go ahead and mount them then if you want to. Okay, LS block is like DF, except it shows all physical block devices mounted or otherwise. So this is a way you can see unmounted devices too. It's very useful when you don't know the drive letter for a device, for example, your pen drive that's not showing up in Ubuntu. Okay, and here you can see a capture of using LS block, LSBLK, and it shows you what it found. Okay, RM unlink. So when we delete a file, we're actually decrementing the link count by 1. So you don't necessarily actually delete the file contents just by deleting a file, because there might be actually more than one link to that file. When the link count is 0, however, the inode is marked as unallocated, and in ext3 and ext4, the pointer to the data block is removed. Unlink is the POSIX function for unlinking. RM calls unlink to actually remove a file's link. So here are some RM warnings. As Derek learned his freshman year, you can seriously damage your computer with RM. Never do a recursive delete, particularly not on your root directory. On the other hand, just because something has been RM does not mean that it's gone forever. You must physically delete it by zeroing the drive. Most people actually don't do this, but you could. So here's an example in this capture below. So you can mount any file, and we've already done that in this course using the file manager in Paladin. We didn't do it from the command line, but this includes input files we DD. And this includes physical drives like dev SDA1. To investigate a partition that we have created a bit-by-bit copy of, we would mount it as read-only, such as sudo mount -o ro myinvestigation.img /mnt. Okay, so you can actually mount these image files that you've created. Unmount, the opposite of mount. We can unmount a device after we've mounted it by running unmount. So sudo unmount and then whatever the mount point happens to be. You can't unmount devices that are busy. And that's going to be true on any kind of operating system, whether it's Linux or Windows. This can be very annoying if a device is busy but you're not aware of it. Okay, I mean, it's going to tell you that the target is busy. Sometimes you have to wait, sometimes you have to close programs that have open files on those devices. So just be aware that that's a real possibility. So here are the references that were used to create this set of slides.